Students, friends, Romans, and countrymen, as I mentioned, the homework number 7 scores for everybody are up. Now, I want to make a note to those of you that got your homework back already through your labs, if you have gotten it back yet. They're going to be, unfortunately, the grader scored them 0 to 4. He's supposed to grade them 0 to 2. And so I corrected that. So the grades that everybody other than OPQR, last names, you're supposed to have 0, 1, or 2 points. And that's what it says. Your paper that you're going to get back in lab might say otherwise. Probably does say otherwise. That's his mistake. But I corrected it in the spreadsheet. So just so you know. Now, I still have grades to post, like for homework 4 and stuff. But everybody now has 7 homeworks, 6 of them for 2 points or less, 1 of them for 8 points or less. All right, and so that's good. Now I think maybe Wednesday or Friday I'll make another assignment, a written homework assignment that is optional that you can use to do a little makeup or a catch-up assignment, okay, which may be helpful for some of you. And it will be due sometime next. If I give it Wednesday, it won't be due on Friday. It'll be due, next week sometime. So we have a little bit of leeway in our schedule now that we've cleared it. Okay, any questions about homework? Yes. It's going to replace something that you designate. So you think of your stinkiest grade, and you can use it to replace that. Now, if your stinkiest grade is like a 0 out of 2, but if the one that I graded is is 2 out of 8, then you can use the homework to replace that one. So there'll be a little space for you to indicate which assignment you want to replace. But I've got to get all the other grades in there, and I'm still kind of staring at a big pile of homework. I also want to say this, and this is with humility, I regret allowing anybody to turn in homework to me through web courses, because once it gets out of the pile, it gets forgotten. And I've got a bunch of you guys that gave me homework, and you don't have a grade yet, and it's because of that. It's just for a class this size, it's kind of difficult to manage this. Okay, so now, quotation of the day. Famous humorist Will Rogers, who was about 80 years ago, 90 years ago, famous guy, got a lot of mileage out of criticizing Congress and a bunch of other people. Never blame a legislative body for not doing something. When they do nothing, they don't hurt anybody. When they do something is when they become dangerous. And we'll have a few more quotes of him for the month of April. A very, very interesting guy. Anyways, last time we thought about the heart as an oscillating biological system. This being the phase space reconstruction of a healthy patient electrocardiogram. They take one cardiogram, and actually they take 10 full beats of the heart, then they analyze it numerically and turn it into a 2-dimensional array. And it's a diagnostic tool for arrhythmias and stuff like that. It's, in fact, catastrophic sudden death arrhythmias like ventricular fibrillation and ventricular tachycardia. We also talked about this energy equation. Here's the energy equation, kind of shifted around to make it look righteous in phase space, where X and P are the 2 coordinates in the graph paper of phase space. Now, the reason I kind of shift, the potential energy there is the X squared term. And it's written X squared over the quantity 2 over K. But no, normally if you're just writing potential energy down and you don't really care about this this form of the energy equation, you just write 1/2 kx squared. And this is the same, that first term on the right is the same as 1/2 kx squared. But this way, it gives you a flavor of an ellipse in phase space. And here's the ellipse all the way. Ellipse is 1 equals, and then x squared over a squared plus b squared over, or plus y squared over b squared. And now this format, when you basically divide this upper equation here by this middle equation here by E, you get this one. And now it's looking like a normal ellipse. And go ahead and sketch this ellipse out. We're going to be talking about it through the wazoo. It is a phase space ellipse to represent the dynamics of an oscillating system. And you can think of it as a spring mass system. The maximum extension to the right, x max comma 0, is out here at the right-hand extreme. And then the maximum rightward momentum is up here. I didn't label it because I ran out of room. I didn't want to make the diagram too cluttered up. But right up here, P, 0 comma P max, maximum momentum. Now I did label these other points. Here's the left-hand extreme, minus x max comma 0. All right? And this is for a perfectly symmetric oscillating system. This one that we were just looking at, the heart, that wasn't perfectly symmetric, but it still is illustrative and useful to look at that phase space reconstruction. It's very good. It's very diagnostic, very powerful. This one's more idealized. The heart has an oblong shape. It doesn't have a symmetric shape. It kind of is. It's a little blobbier than. Like the lungs are pretty symmetric. There's a left lung and a right lung. And then what else do you have? Your kidneys are basically symmetric. You got a left kidney and a right kidney. Your eyeballs, most people have, some people, did you know that some people have one color eyeball and the other color another color on the other side? But eyeballs, but the heart is not perfectly symmetric. Anyways, and then up here is just a generic point at some time t, x of t, comma p of t, the coordinates at that time t. And then down here at the bottom, 0 comma minus p max, again, assuming that the momenta are behave symmetrically for this spring system. The way that this works, in geometry class, this denominator here under the x squared is the square of half the width, what we call the semi-major axis, in this, for an ellipse that's oblong this way. So this denominator here, 2e over k, is equal to x max quantity squared. You might want to write that down. I didn't put it in here, but yeah, it's definitely true. Similarly, in geometry class, the y squared term is y squared over b squared, and b is the semi-minor axis, in other words, the vertical axis in this case, or it's half that. Okay, so that's this one here. So p max quantity squared is equal to 2e times m. All right? And guess what that means? The maximum energy is equal to P max squared over 2m. In other words, the maximum kinetic energy. P squared over 2m is the kinetic energy. And basically, that's where we got this. P squared over 2m. This is kinetic energy term right here. The second term in this, in each of the right-hand sides of the equation blocks. And so you can see how these two, the limits of the motion, its limit in the x direction, its limit in the momentum direction are encoded into the energy equation in this way. Now, another thing that I want to mention to you is, and that we're going to talk about a little bit, is the area. The area of an ellipse is simply pi times the semi-minor axis times the semi-major axis. Now, if your ellipse is actually a circle, A is equal to B, and we don't call it A and B, we call it R. You know, a perfectly symmetric ellipse. It's not, you know, it doesn't look like a football or an egg. It's just a perfectly circular ellipse. You know, the semi-major axis equals the semi-major axis. We call it R. The area is pi r squared. But if you have an oblong one, it's similar. It's just pi times whatever the semi-major axis is times whatever the semi-minor axis is. And you probably didn't learn that in high school, but it's true. And it requires a little bit of trig and a little bit of calculus to prove that, but it's not too bodacious. And anyways, applied to this dynamic phase space ellipse, that's pi times x max times p max. All right. And so again, the area of this ellipse is related to the product of two of the dimensions and then a factor of pi. Okay. Now, what we're going to, let me pause for questions here. Yes. Yeah. X max is also the square root of 2e over k, that parenthesis underneath the x squared term. Yeah, that's right. So, so 2e over k is equal to x max squared. You know, so there's an enormous amount of information encoded into a phase diagram, especially for an oscillator because of so much symmetry. You know, we could do a phase diagram for a falling stone. It's not that interesting. It just kind of tails off into bigger and bigger momentum. But this one is limited momentum and limited spatial containment. So this one's this one exhibits containment. And for those of you that are have taken chemistry and will take chemistry, the entire quantum hypothesis is activated in systems that experience some kind of physical containment in the x domain or in the momentum domain or both. And that's you know, you won't see that until you start studying, you know, like physical chemistry or something like that if you haven't. Anyways, let's do a clicking questions. And what we're going to do, you might want to take notes as we go. We're going to use the same ellipse, and I've labeled most of the points on it now. And what we're going to do is trace out the position and force and velocity, or actually we're going to kind of think through the position, force, and velocity in the next few questions. So let me pause the recording, and let me get the cursor over here. Okay, so here's your first question. You pull the mass out to x max comma 0, and you hold it, right? So v is equal to 0. When you let it go, it will begin to acquire what? So in other words, you start it out here at x max comma 0. There's no other way to interpret this position out here, by the way, except somebody holding it and then releasing it, because the momentum is 0. It's at rest. But then it begins to acquire something. Okay, 30 seconds, starting now. Good. I'm starting to see people thinking with their hand. I like, I grew up by an Italian neighborhood, so we used to see people talking with their hands. And I love seeing you guys thinking with your hands. It's good. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Yeah, most of you got this correct. The answer is uh, momentum to the left. Yeah, and here's the, if you got tripped up, a few of you did. Here's the reason. Because if you're out there at X max, you're off to the right somewhere, right? So it's a spring system. So if you're out to the right, the force is back to the left. So your delta P is leftward. Delta P over delta T, that's the force. So you're going to, at least for the first few seconds or first few milliseconds, depending on how fast your oscillation goes, you're going to be acquiring leftward momentum. All right, next question. Since the mass develops leftward momentum, make a decision. A, B, C, or D? Ah, good. I see people going like this and going like this and stuff with their hands. Good, good. That's what I love seeing. I keep seeing people go like this, but not everybody. Lovely. Students thinking. From the front row to the top row. Nice. Okay, 20 seconds. 15 seconds. Ooh. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh, you know what, my wonderful students, we got some, whoops. Go back. That's the previous question. I'm trying to get this over. What is, what does it keep doing that? There's a, anyways, the main thing, let me go back. I'll just try to describe this without using the results. Okay, so here's your question, right? Now, I'll just verbally describe it. There was a mixture of results, and there was not a majority on the correct answer. Okay, 19% voted for A. That's up there in the second quadrant. 23% voted for B. That's up there in the first quadrant. 41% voted for C. That's down in the fourth quadrant. And 60% voted for D. Now, when that happens, it tells me that that you as a group have still got to make the decision clearly. There's a little bit of leeway in your answers. You know, in other words, it's not like 90% getting the correct answer or 90% getting the wrong answer. You know, that would be a wrong decision. So what we got here is a little bit of difficulty. Now, you're developing leftward momentum. And so in a one-dimensional momentum axis, left is negatory, right? So that means the first, you know, you start out over here. Let me get my cursor back over here. You start over here with zero momentum, and then you develop negative momentum. So what that means is that you're right here, somewhere down in the fourth quadrant, right? So point C, go ahead and make a note of that. And this is significant. You know, the other ones, this is where it goes first. You know, if you started out there, maximum rightward position, the force is to the left. It doesn't have any momentum, but it's getting leftward momentum, which dips it down below. And then you know what happens? You know the rest. It dips all the way back around. So really, you now have a direction of motion for the entire system in phase space. Now, this is not where you would see it move if you were taking a movie of it. All right. You know, a movie of it would just be going back and forth, left to right, right to left, left to right, right to left to right. Okay, that's what a one-dimensional oscillator does. And you guys have been doing those in the labs, or have done those in the labs. But in phase space, remember, this is an abstract representation. But you can still say that the oscillator is moving in phase space in the direction of the arrows that I've got. So go ahead and put a little circulation arrow, a couple of them, on the phase space diagram. Now, this is an important distinction, and one of the main reasons I think it's important is because it basically encodes the direction of time. There's a couple other ways to encode the direction of time. One of them is thermodynamically, what we call the thermodynamic arrow of time. And hopefully we'll get to that this semester in another couple weeks. But this definitely tells you, in other words, an oscillator in this plane, in this universe, is going to go clockwise on this diagram. And if you were to start it out over here to the left from rest, it would just be a mirror image. It would start acquiring, it would have a rightward force. If it was out here to maximum leftward compression or whatever it is, it would have, you know, maximum left position. It would have a rightward force. It would start acquiring rightward momentum. So when it would start, you could start it here. That's no problem. But then it would dip upward and go immediately to X max. Also, make a note. Maximum kinetic energy is at X equals 0 for a harmonic oscillator. There's no force acting on it for that instant of time that it crosses X equals 0, but the kinetic energy is the max. Potential energy is 0. Now, the 0 of kinetic energy is out to the left or right. That's the turning point. You have 0 momentum, you have 0 kinetic energy, right? So there's a lot of other things. Now, there's one more thing about this ellipse that I want to talk about, and that is the area, all right? Now, I have another clicker question for you. Go ahead and write down this equation if you haven't already. The area of a geometry class ellipse, pi times a times b. Phase space ellipse, pi times x max times p max. All right. Next question, multiple choice. What is the measurement unit? You know, that you would need calculus, or you'd have to know the formula to calculate the area, but it's, you know, so it's not square centimeters or square meters, but it does have a unit of measurement. 30 seconds, starting right now. Boy, this thing's really blooped up. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Stop. And yeah, if you voted for C, you got that right. So write that down. The area, the area of the phase space chart, the ellipse, in phase space, it's angular momentum. Where did that come from? You know, it's not rotating, it's just oscillating back. But you know, we relate to oscillation to a circle or an ellipse. So in the abstract, you can think of it as having kind of an abstract rotation. Now let me bring one more point up to you. Angular momentum, especially in this diagram, has a physical significance. Angular momentum is the unit for measuring Planck's constant. And if you've taken a little bit of chem, raise your hand if you've taken chemistry and heard of Planck's constant before. Okay, this is where it all began. Planck was studying oscillators. The area of these babies in phase space is measured in units, and you know, Planck, here's the famous concept. H bar, or H, Planck's constant, the one constant to rule them all. For some reason, in every physical process in this world, Planck's constant is involved. Every electromagnetic interaction, gravitational interaction, the two nuclear interactions, Planck's constant is essential. You know, the two nuclear interactions, you don't need Newton's constant, capital G. Speed of light, you don't need Newton's capital G. I mean, you need it for electromagnetism, but you don't need it for the gravitational interaction. But for all of them, you definitely need H, Planck's constant. Now, hopefully, when we get a little bit deeper into thermodynamics in a week or two, we'll talk a little bit more about Mr. Planck, Professor Planck. But now what I want to do is get to oscillation periods. All right, so this is a little bit instruction actually from chapter 16.2 and 16.3. And there it says there are two important factors. Two important factors do affect the period of a simple harmonic oscillator. So if it affects the period, it affects the frequency. And omega is the angular frequency. The period is related to how stiff the system is. So in other words, if you have a really stiff spring, the period, it's going to oscillate really fast. And so the period is going to be small. The frequency will be big. Number two, the more massive the system is, the longer the period. So if you have a regular spring and you put like a ton of uranium on one end in your mass, it's going to go really slowly. All right, it won't oscillate, because the spring won't be able to, the spring will cause it to oscillate, but not very fast. All right, so the longer the period, and therefore the shorter the frequency, smaller the frequency. Now, let's take a look at that. So stiffness of the spring, that's in the spring constant K. And then the mass that encodes the inertia. Now, here's a diagram from 16.3. This is figure 1. And you know what? I like this diagram a lot because I've never thought about an oscillator just this way. What they've done here, they've done pictures, and you can, let me get my cursor over here. Okay, you can see over here, they have a picture of a spring on a mass and a red arrow for the force, V equals 0. They have all that stuff, kind of like what I was doing last week, Wednesday and Friday with you guys. And down here, here's max compression. And out here's max extension and stuff. But you know what they add? Look at this. They add the free body diagram. And that, I think, is nice. Because, and we kind of alluded to it, out here at max extension, you have a leftward force. And of course, you have the normal force from the tabletop upwards and the downward force of the weight balancing. But now here, as it passes through equilibrium, you don't have zip zap for a horizontal force. Still have the normal and the weight force. All right, can't, you're not going to get rid of that. Question?
Wouldn't it be more accurate to represent the leftward force and the rightward force as the same magnitude?
Yeah, they're supposed to be the same magnitudes. These red arrows, they're only drawing them at maximum extension or max compression. So I think these arrows, don't they look the same? I mean, I'm kind of looking at it as slant here. They're like the same size.
No, I'm saying the top two on the right side.
Oh, here? Oh, you mean in the free body diagram? Oh, over here?
No, the right.
Over here?
They don't have a force diagram on the left.
They don't. Over here, there's no horizontal force when they're passing through equilibrium. X is 0, so the spring force is 0. Once you dip to the left of that, then you get some rightward force over here, right? So, no, it's because it's a spring. It's an oscillating system with a restoring force. So at equilibrium itself, zip zap for force, because it's proportional to X, the displacement away from equilibrium. So if you're not displaced from equilibrium, you don't have any force. The spring is just kind of resting there. All right, so that's why that is. Okay, now the angular frequency that we've been talking about, it's actually the figure of that identifies, a lot of scientists will think about the angular frequency of a system as its ID. So you might have a physical spring mass system like in a clock, an old-time clock where you have to wind it up and stuff. Although most clocks now that you buy down at Walmart, they're battery run from China. Electronic oscillator. Now, this one, we definitely have bazillions of these. Electronic oscillator, for instance, in a radio transmitter or a radio receiver. Or anything that takes a signal and turns it into audio, or takes audio and turns it into a signal, is going to have oscillator circuits. And the difference between these two is, as you'll learn in 2054, by the way, I am going to be teaching 2054 in the fall. I just got the confirmation from my BOSS today. So for those of you that want to sign up, go ahead. If for those of you that want to avoid it, go ahead. God bless you. You don't have to take my class. And if you can't take it because you don't, it doesn't fit your schedule. You know. Anyway, what you'll learn in 2054 is that we have electronic circuits and that oscillate. If you know what makes them oscillate, they have to have a basically a battery, a capacitor in the system. And if they have a capacitor and a magnet, they'll oscillate. Some kind of electromagnet in the system. And a photon, we could consider a photon as an oscillating system. And guess what? Its energy is h bar, Planck's constant, times omega. So the photon energy, yeah, h bar omega. We think about that out the wazoo. And a huge amount of relativity is done in terms of not the energy, but the omega. If you're working with photons, anyways, in terms of the omegas, it's just a little bit easier to work with. Okay, now the formula for like a spring mass system or anything else, omega is the square root of k over m. Now remember, here's the interesting thing. You know, in a photon, the oscillator is h bar times omega. So that's the energy. So energy and omega are proportional. Now look at this formula here. The denominators of the ellipse equation, one had k in it and the other one had m in it. And the omega formula's got both m and k in it. They're square rooting it. Does that make sense to you? Yeah. And you can work it out. You know, matter of fact, you could restate the oscillator ellipse equation in terms of omegas. And, you know, it'd be kind of cool to do that. So, and now, the other equation here is just kind of a reference. This is how I always remember the difference between omega and frequency f and period t, capital T. Okay, and go ahead and write this down. The frequency is 1 over t. And that's the regular frequency that we label f. All right? So f is 1 over t. The angular frequency is 2 pi over t. All right? And here's the key fact. Omega times t is always 2 pi. That's how I remember that last thing. And then I figure out, you know, the f's and everything else. All right? Now the reason that that's important and the reason that we use omega a lot is because we have a lot of trig functions to work with in oscillating systems. You know, so if you're working with electromagnetic radiation, photons, anything, you know, small oscillations in an appliance that oscillates, you know, kind of oscillates like this. Sines and cosines, sine of omega t, 0, because sine of 2 pi is 0. Cosine of omega t is 1. So this helps us keep our sines and cosines squared away, you know, using omega instead of f. But if you want, you could write 2 pi f times t equals 2 pi, because f times t is equal to 1. So it's, you know, but this is the way that I remember it. Okay. Special 5-point bonus question. No, she still went. Okay. Psych, I wasn't going to do that. I try to juke people as they go out the door. We're going to dismiss. Read as much of chapter 16 as you can. And I'll see you on Wednesday, and we'll think about homework. Oh, America's Most Wanted. If you didn't, and also, last name's OPQR. Come up and get your homework if you haven't already done so. Special bonus question, 5 points.